Hello everybody, this is Dr. Nurbat Shah from University of Engineering and Technology, Peshawar. In this series of lectures, I'll be mainly talking about calculus. I'll be following Thomas and Finny book for solution of some questions. So in the first lecture, I'll talk about functions. What are functions and what is the domain of function? And I'll be talking about some well-known graphs. So first we define what is function. Function is from a set A to set B. It's a characteristic which define a correspondence between every element of first set to a unique element of the second set. If we talk about calculus or we talk about functions defined in calculus, which we usually call real valued functions, in that case, both the sets A and B will be subsets of set of real numbers. The notation used for a function that is f of x, where x is the input for that function and the output is usually represented by y. More generally, we write the function as y is equal to f of x, right? We can say this is our dependent variable, whereas f is representing the rule, the correspondence by which we basically map or match the two sets. X is the independent variable, independent it means that is free for us, we can give any value to this x, whereas y is depending on the value of x. For example, if we define a function like y is equal to x square, so in this case this f is basically what? That is square of anything. If we take y is equal to x square, I would put the value of x to be any real number, right? So I can take x is equal to 1. That's obviously I have a freedom to take the value of x. So if you take x equal to 1, what would be the value of y? Can I take the value of y 2? The answer is no, I can't take that because y will be depending on x and the correspondence as well. So I'll be simply taking 1 square, that is equal to 1 as well. If I take x equal to 2, I am taking x equal to 2. Now the question is, can I take x equal to 3? The answer is yes, I can take x equal to 3 as well. But for this x equal to 2, I will take only 2 square, that is equal to 4. Similarly, for x equal to 3, I could take only 3 square, which is 9. So that's why we call this one as a dependent variable, whereas x is independent variable, because we are free in the selection of x, whereas y is depending on the value of x. So that's why we call a dependent variable and independent variable, where f is the rule. There are some other names used for them as well. We do call that as a range variable. We call this one as range variable, whereas corresponding x will be known as domain variable as well. Right? We can call this one as our output, whereas x will be termed as input. Right? We also use the value of y as image, whereas x will be termed as pre-image. keeping one thing in mind, that we can use all these notations or these names in parallel or in group. When you use mh for y, you will be using pre-mh for x. If you are using output for y, you will be using input for x. If you label y as our dependent variable, you will be labeling x as our independent variable. Right. So this is our output, as I explained. This is a function defined, and this will be input. Right. We usually express function in three different ways. Number one, function could be written in order pair form, which is usually the discrete form. For example, you say for x equal to 1, I'll be having y is equal to 2. For x equal to 2, I can have y is 4. For x equal to 3, I can have value 6. For x equal to 4, I may have 8, and so on. This is one way of expressing a function, right? Another way of expressing this function is a formulation or a formula or a rule, like we write a function in the form y is equal to x square plus 2x minus 6. Whereas a third way, that's the geometrical representation, like we have a graph for something like this is straight line, right? We can have another graph like this one, right? So we can represent a function in three different ways, right? This is a discrete way of representing a function, or the order pair ways of representing a function. This is a formulation for it, a mathematical expression, or explicit or implicit expression for a certain function, and that's a geometrical representation of a function. In each case, how would we know whether a relation is a function or not? Like if you are given a relation in this form or in this form or in geometrical form, how would you know whether that relation, that correspondence is defining a function or not? Usually, this type of representation for a function, where we have 1, 2, 2, 4, 3, 6, this could be written in this form as well. Like see, we have one set here A, we have another set here B. So we take some values from here 1, 2, 3, 4, let's suppose, whereas we have 2, maybe 3, maybe 4, maybe 6, maybe 8, and so on. And then we do some correspondence like that. 1 is going to 2, 2 is going to 4, 3 is going to 6, 4 is going to 8. So we may write this representation of a function in this form as well. Now, how would we know whether it is a function or not? So as I define the function, we say for every element of this set, there will be a unique correspondence in this set, in the second set. Like for 1, we are having 2, for 2 we are having 4, for 3 we are having 6, for 4 we are having 8. So for every value of this one, we are having a unique value here. So this is defining a function. If we had an expression like that for 3, let's suppose if it was 3 as well, like that. So you see, for one value of x, we are having more than one values of y. So in that case, this expression will not be a function, right? So here are given some examples in that explicit in a discrete form, and we want to check whether they are a function or not. So this first example, you see, in 2006, the total number of iPhones sold are what? That's 0. For 2007, we are having this is a cumulative, obviously, number of iPhones. In 2008, that's this one. So you see, every element of this set is being corresponded to a unique element in this set. See, there is no repetition. For in simple concept, in simple words, if you are having an expression like that from one element of a set A, if you are having a V shape like that, so we say it is not a function. If you are having something like that for B, we see this one and this one, that's okay. This is allowed for a function. So in this case, you see that we are not having two values for one value of domain. So therefore, this is defining a function. What about this one? Again, every element of the domain or every element of this set is being corresponded to a unique element of this set. You can see that this 5 and minus 5 both are taking same value 25, but it is allowed in a function, right? Whereas in part C, if you see for these two, this value is got two values, that is clubs and that is got White Sox as well. So in this case, this expression is not defining a function. Whereas this one is also defining a function because every element of this set is being assigned a unique value from here. Yeah, cubes and White Sox, they have obviously a same value, but that is still a function. Okay, these are some more examples of functions. So we can simply go for whether they are function or not. So we say a family is the set A. The corresponding is basically done with what? With the person weight, and that is basically producing a positive number. Right? So you know that for every family member will be having some weight, and that weight will be obviously a positive real number. So this is defining a function. The integers, and taking its square is obviously defining a non-negative integers. Right? So it is also defining a function. The set of all states and each state's member of the US Senate and the set of all US senators. So you see from all states, right, every state has a Senate member, right, and then we have the set of all US. So again, obviously you see that it is defining a function as well. So more generally, what is function? So function is basically like a machine where we have an input, and for every input there is a unique output. Like in this case, we are basically entering a circle into the machine, and that is producing cubes for us. So for every x there will be a cube for us. Right. The second type of function is explained, that is a geometrical representation, right? So geometrical representation of function, if it is given, how could we check whether it is a function or not? For that purpose, we do what? We use a vertical line test, right? How do we do? What's the procedure in that case? If every vertical line crosses the graph of a relation in exactly one point, we say it is a graph of a function. But if you could find one vertical line which passes through more than one point for a certain graph of a relation, it will not be a function graph. Let's do some examples and we see whether they are function or not. Right, this one. Now we check. If you see every vertical line is crossing the graph at exactly one point, so it is a function. What about this one? Again, if you draw a vertical line, so every possible vertical line is crossing the graph of this function at exactly one point, so it's also defining a function. If you draw a vertical line, right, so you see the vertical line in this case is, if you consider this vertical line is one of them, so this is crossing the graph at this point, and it's also crossed the graph at this point as well. So this vertical line is crossing the graph in more than one point. So this is not a function graph. So more examples. You see, if you draw a vertical line, any vertical line would be crossing this graph at exactly one point. So it's also a function. What about this one? If you see the vertical line itself is crossing this graph at more than one, it's basically crossing the graph at infinite points. so it is not a function. What about this one? You can just ask yourself whether it is a graph of a function or not. But again, every vertical line will be crossing the graph at exactly 2 points. So it's not a function graph. What about this one? If you draw any vertical line, every vertical line will be crossing the graph of this relation at exactly 1 point. So it is a graph of a function. Okay, just a practice for you. You just maybe pause the video and you could just ask yourself whether they are graph of a function or not. The first one is obviously a graph of a function, because if you draw any vertical line, it will be crossing it exactly at 1 point. So this is a graph of a function. Whereas in this case, if you draw a vertical line, this vertical line is crossing the graph at more than 1 point, so it is not a graph of a function. The same story here. If you draw a vertical line, it will be crossing the graph in more than 1 point, this point and this point. Even so, if this y-axis is crossing the graph at more than 1 point. So again, it is not a graph of a function. What about this one? So again, you see, if you draw any vertical line, it will be crossing the graph in exactly 1 point. So it is a graph of a function. The same thing, it's also a graph of a function because every vertical line will be crossing this graph at exactly 1 point. What about this one? If you see, if you draw a vertical line here, it crosses the graph at 1 point. If you draw any vertical line on the right of this point, again it crosses at 1 point. But if we draw a vertical line here, right, so it is crossing the graph at this point and at this point. In this case, you see, we are having a simple hole where this is a bullet point. So it means the function value at this point is what? Is this one, it's not this one. So it is a graph of a function, whereas in this graph, at this point, the function will be having two values, is this one and this one. So for one value of x, we are having two values of y. So it is not a graph of a function. Before I move towards domain and range, I just talked about a function which is defined by a formula like y is equal to x square, right? It's a relation, and we will be talking about whether it's defining a function or not. Let's suppose we have y is equal to under root x, right? We can have a function y is equal to x absolute. We can have a function y is equal to y absolute is equal to x, or we can have x absolute is equal to y absolute. Maybe we can have x square plus y square is equal to 9. So these are the formulas for certain relation, and then you can talk about whether it is a function or not. So the procedure, the test used for checking whether a formula is defining a function or not is you would simply put one value of x from your side, right? Let's suppose I take x is equal to 1 in this case, and I put the value in the given function or in the given relation formula. If it gives me exactly one value for all values of x, that would be defining a function. So we cannot find a one value of x when we put it here and that gives us more than one values of y. So then we would say it is not a function, but in this case it's a function. In this case, if you see y is equal to under root x, so under root x is basically, you know that it is defined for positive values only. So if I put x equal to 4 or x equal to 9, what would be the value of y? I'll be taking only one value, and that is what? That is 3. So it's also defining a function. If you put x equal to 1 here, I'll just get one absolute. So one absolute is equal to 1. So therefore, it gives you one value. If you put x equal to minus 3, it gives you y is equal to minus 3 absolute, which will give you plus 3. So it is obviously defining a function. Whereas in case of this function, this relation or this formula, y absolute is equal to x. Now, if you put x is equal to 1, what would happen? y absolute is equal to 1 because I've taken x equal to 1. So what would happen? Absolute of a number is 1 when that number is either 1 or minus 1. So for one value of x, we are having two values of y, therefore we say it will not be a function. Similarly, if you consider this x absolute plus is equal to y absolute, so if you put x equal to 1 or 2 or 3, whatever it is, or minus 1, so if you put x equal to minus 3, what would happen? It becomes y absolute is equal to plus 3 because minus 3 absolute is equal to 3. And when we want to get rid of this absolute, it will give us two values, plus 3 or minus 3. So for one value of x minus 3, we are getting two values of y. It's 3 or minus 3, therefore it is also not defining a function. What about this relation x square plus y square is equal to 9? The procedure is same. I may take x equal to 0. You can take any value. You just need to find one value for which the value of y is repeating. The y square is 9, and then you take square root on both sides. That will give you plus minus 3. So again, it is not a function. Okay. So conclusion is that for every value of x, or for the value of y must be unique if it is a function. If you could find one value of x for which the function value is repeated, we say the relation is not a function. The next basic concept in function is what that is domain. So domain is what? That is for a certain function. It could be a relation as well. We can talk about both. It might be a function, it might be relation as well. Domain can be found for both things, right? So how do we define first domain of a function? So it is the set of all input for a certain function where this function f is defined. When we use the word defined in calculus, that would mean the value of y should not be infinity. The value of y should not be a complex number. It should not contain iota something. And it should not be an indeterminate form, 0 by 0 or infinity minus infinity or infinity by infinity, 1 power infinity. These are known as indeterminate forms. So those values for which y is giving you infinity, or it gives you a complex number, or it gives you infinity minus infinity or 0 by 0 or any indeterminate form, they will not be included in the domain. So any real number for which y is giving you a defined value, it will be in the domain. So for example, if you take y is equal to 1 over x minus 1, right? So this function is defined everywhere except x equal to 1. If you put x equal to 1, what happens? It's 1 minus 1, that give you what? Infinity. So as I said, at x equal to 1, the function is not defined, therefore its domain will be all real numbers except 1. Similarly, if you consider y is equal to under root x, so under root x is only defined for x greater than or equal to 0, because if x is less than 0, what happened? Under root x will lead you towards a complex number, or maybe called imaginary number, which is not not considered acceptable in real analysis or in calculus. So it means domain of this function is what? That would be all non-negative real numbers from 0 to infinity, including 0, because it is defined for x equal to 0 as well. Okay, and what about the range? A range is basically the set of all values of y for given values of x. When you put value of x in the given function f, it would give you some output, and then we collect that output and write that in a set form just to give you a range. So it is the set of all values of y for given values of x in its domain. We cannot put the value of x out from outside the domain, right? So if we talk about this function 1 over y is equal to 1 over x minus 1, okay, so the procedure To find a range for a certain function or certain relation, what do? We simply solve this expression for x. I might write this one as 1 over y is equal to x minus 1, or we can write x is equal to 1 plus 1 over y, which could be simplified as y plus 1 divided by y. Now, those values of y for which this relation is defined will be included in the range, or those values of y for which this relation is not defined will not be included in the range. Now you see x has become y plus 1 divided by y, so this is defined everywhere except y is equal to 0, so we say its range will be all real numbers except 0, because this function will never give you 0, 1 over x minus 1. So its range is what? That is all real numbers except 0. If you talk about the second function we consider, y is equal to under root x. So you know that, again, as I said, we will express this a function is in terms of x as a function of y. So we'll be having x equal to y square. By this case, there is a point that this relation is defined for all values of y. So by using that concept, it means that the range will be all real numbers. But that's not right, because in this case we are given a positive square root. We are not considering negative values in this case. So therefore, the range of this function will be positive and including 0 as well, which could be written in the form 0 to infinity. So this function range will be what? All, again, non-negative real numbers, because from here you will just get some idea about the range. Then from this relation, getting some information from there, getting some information from the function nature as well, collectively we can find a range of that function. Let's talk about some well-known functions whose domain and range are defined here, like y is equal to x square. Now you see, y is equal to x square is defined for all values of x. Whatever the value of x is, its square is defined, so it is all real numbers, which could be written in this form as well. So all real number is the domain. What about range? As I said, y is equal to x square is the function. Can I solve this for x? So I can do that. So it's plus minus under root y. Now we know that square root is only defined when it has a non-negative value. So that means y is greater than or equal to 0 is the range. So the range will be set of non-negative real numbers. As we discussed in previous case, 1 over x. So all real numbers except 0, because its denominator will be getting 0 at x equal to 0. So all real numbers except 0, whereas the range is also the same thing. We discussed already y equal to under root x, so the domain and range both are non-negative real numbers. What about y is equal to under root 4 minus x under root 4 minus x, sorry. So to find its domain, what would happen? You would simply take anything inside a square root must take positive value. So you'll be taking 4 minus x is greater than or equal to 0, okay, which gives you x will be less than or equal to 4. That means all real numbers which are less than or equal to 4, mean to say starting from minus infinity and going up to 4. What about range of this function? It is using a square root for this function. See, so we take y square, we just get rid of the square root to get 4 minus x. Or we can take x is equal to 4 minus y square. Now, keeping in mind that this function is defined for all real numbers. But if you look into the function will never give you negative value, because we are given only positive square root. So therefore, we'll be taking only positive real, non-negative real numbers. Let's talk about this one. Y is equal to under root 1 minus x square. So for domain, anything inside a square root that must be positive or non-negative, 1 minus x square should be greater than or equal to 0, which basically leads us towards an equality, quadratic inequality, x square is less than or equal to 1. And that is only possible when x is between minus 1 and 1. So domain of this function will be what? That will be all real numbers between -1 and 1. Keeping in mind there are infinite number of real numbers between -1 and 1. What about range? The basic concept of range is same as I explained earlier. What do? We will simply take square of this to get 1 minus x square, because we would be expressing x in terms of y to find the range or some idea about the range. So you see from here what happens, can I write that as x square is equal to 1 minus y square. I would take a square root from here to get the value of y, that's plus minus under root 1 minus y square. Whatever inside a square root must be greater than or equal to 0 if you want to have a real number. So that means y square is less than or equal to 1, which means minus 1 is less than or equal to y is less than or equal to 1. So it gives us just an idea that the range can never be outside -1 and 1, but the function is defining as a positive value, so we just ignore in this case negative value. So range in this case will be what? Starting from 0 and going up to 1. We are neglecting the part from -1 to 0. 0 is included, so that's why I'm just using parentheses because of this positive square root. If it was given as minus, right, under root 1 minus x square, then we'll be taking this one as our range. It will be from -1 to 0, right? Sometimes we may have a relation like that. Y square is equal to 1 minus x square, or we can write x square plus y square is equal to 1. In this case, domain will be exactly the same. It's from -1 to 1, and range will also be taken as -1 to 1. Because in this case we are allowed to use both values, to take both values, negative, positive as well. So in this case the range will be -1 to 1. The next type of function that is known as a piecewise defined function. The piecewise defined function are those functions which are defined by different formulas in different intervals. The well-known function is x absolute. You know that, that's a simplest one and a well-known function. It is defined as x when x is greater than or equal to 0. Its value is minus x when x is less than 0. So you see, if x is greater than or equal to 0, its value will be taken as x. When x is less than or less than 0, it will be taken as minus x. So this is an example of piecewise defined function. So a function that combines pieces of different equations, or we say that in different domain or in different region and different interval, the function is defined by different formulas or different relation. We call it piecewise defined function. Keeping one thing in mind, this is if you take this example, this is as a whole, it is a one function. It's not like that it's a two function, it's a one function. If you are given a relation like that and you are asked what is f of 1, so f of 1 basically means you have to look for the domain. 1 is always greater than 0, you know that, so we'll be using this formula. So that is 3 into 1 minus 3, that would give you 0. If you want to find f of 0, so you see 0 is neither included in this interval nor included in this interval, so you would say f of 0 is not defined, that does not exist. That's why in graph you see this is a whole and this is also a whole. Okay, so therefore we say f of 0 does not exist, right? If you want to find f of -2, so -2 is less than 0, therefore we would simply use this formula. So minus into -2 plus 2, that is equal to 4, and so on. This is another example. The function is defined as f of x is equal to minus x when x is less than 0. Its value is x squared when x is between 0 and 1, and its value is 1 when x is greater than 1. Right? So in this case, if you want to find the values of every value of function f of x at different points, so if you take f, what is f of -1? So -1 you see that is less than 0, so you'll be using this formula. That is minus into -1, that's plus 1. If you want to find f of 1 by 2, so 1 by 2 is in this interval, in the second interval here, so we'll use this formula, that is 1 by 2 square, which is equal to 1 by 4. But if you want to find f of 4, so 4 is basically greater than 1, so you'll just take its value to be 1. So f of 4 is equal to 1. And that's the graph of this function, because for the left it is just a straight line, it's minus x. Between 0 and 1 it's a parabola, and after 1 it is simply a constant function, y is equal to 1. This is another example of piecewise defined function. These are some well-known piecewise defined function as well. The one that is known as greatest integer function, which is denoted by this the notation used for it, right? And that is giving you all, if you take all integers which are less than or equal to that number, and then we take the biggest one among them. It means like that, if you see, if I want to find greatest integer value of 6.5, so all integers which are smaller than 6.5 are 6, 5, 4, 3, 2, and so on, and then the largest among them will be what? That would be 6. If you have 3.1, even the 3.01, right? So the smallest integers are 3, 2, 1, 0, and so on, and then the largest among them will be what? That is 3. So 3.01 will give you what? That will give you 3. If you take simply 3, so the greatest integer value in this case will be what? That's 3, again 2, 1, 0, and so on. The largest one will be what? That will be 3. Mathematically, we just define it. If x is between minus 2 and minus 1, it will give you what? It will give you minus 2. Matlab, mean to say, any value between minus 2 and minus 1, excluding minus 1, would give you minus 2. And anything between minus 1 and 0, that would give you minus 1. Anything between 0 and 1, that would give you what? 0. And anything between 1 and 2, it will give you 1. So if you want to draw a graph of this function, so you see it will be like that. I just draw it arbitrarily. If we are between 0 and 1, so let's suppose we have 0 here, this is 1, so the graph between 0 and 1, its value is what? That is 0. It's open here, okay, and this is 1. If we go to 2, so between 1 and 2, its graph become what? Its value become 1. So we just take bold part here and open here. Similarly, for 2 to 3, the graph will be starting from here and open part here. This will be bold, keeping in mind. This part will be bold. This part will be bold. And so on. The same thing, the graph will be going here, then we have here, then we have here. This is the graph of what? Greatest integer function. Okay, let's have some well-known relation about Gauss greatest integer function, GIF. That is, for any small positive number and any integer a, so if we take a plus h, that would always give you a, whereas a minus h, that will give you a minus 1. What does it mean? For example, if we take minus 1 plus 0.01, so minus 1 plus 0.01, that means we are in this interval now. Minus 1 plus 0.01, so we will be in this interval, you see. Sorry, it's just, we just take, if you take a plus h, so that will give you a in greatest integer, so it will give you minus 1. And if you have minus 1 minus 0.1, so in that case we'll be taking what? It's minus 2, right? Okay, and then we go to the next function that is known as least integer function, which is defined as that's the smallest integer among all the largest ones. As I explained earlier, if you take 6.3, the notation is this one now. So we take all integers which are greater than or equal to 6.3, so that is 7, 8, 9, 10, and so on, and then the smallest one among them is 7, so 6.3 least integer value will be what? That will be 7. Mathematically, we define that as if x is between -3 and -2, its value will be -2. If it is between -2 and -1, its value will be -1, and so on. And the relation, as I explained in the previous case, would be what? A plus h, least integer value will be a plus 1. We might use this notation later on when we find limits, so you should keep this in mind. So a plus h, that will give you a plus 1, whereas a minus h, that will be a. This is an example. -1 plus 0.01, that will give you now 0, whereas -1 minus 0.1, that will give you -1. H must be very small, keeping in mind. Okay, now let's talk about some well-known graphs. The first one is for powers of x with x equal to 1, x equal to 2, x equal to 3, x equal to 4, x equal to 5, and so on. So these are the well-known functions. Obviously, we can later on go for combination of combination of these functions, and then we draw the graph, right? So first, if we take n equal to 1, the graph will be simply a straight line because it's a linear function, and graph of a linear function is a straight line. If we take n equal to 2, it becomes a parabola, so it will be y equal to x square, and the graph is obviously look like that. For n equal to 3, the graph will be like that. It's a y is equal to x cube. The graph of y is equal to x power 4, that would be something like that. That's the shape of it. You should keep this shape in mind because later on obviously be having different type of functions. And for x equal to n equal to 5, the graph will be what? It will be like that. We can have the graph for negative values as well. If you have y is equal to x power n with n equal to -1, the graph will be like that. Where for n equal to -2, it's 1 over x squared and 1 over x graphs, right? So these are the graph for n equal to -1. This one is the graph of 1 over x, whereas this one is the graph of 1 over x squared. You have to keep these graphs in mind. Later on, we may require that when we do scaling and shifting of functions. If we take these powers 1 by 2, which is square root, 1 by 3 is a cube root, then we have a cube of square root and square of cube root, the graph will be like that. This is graph of y equal to under root x, right? This is the graph of under cube root of x. Here is the graph of cube of a square root, whereas this is the graph of square of a cube root. Right, so these graphs are very important. These are well-known graphs, and obviously later on we may need these graphs in a case when we do shifting of graphs or we do scaling of graph, etc. So you have to keep these functions or the graph in mind. Okay, these are the graphs of exponential and some logarithmic functions, right? So if you take y is equal to 10 power x, that's a yellow graph. 3 power x and 2 power x, as you decrease the value of the base, the graph will be obviously getting closer towards x-axis. Whereas for 10 power minus x, 10 y equal to 3 power minus x and 2 power minus x, we are be having the graph in the next direction. And these are the graphs of log. You keeping this in mind that log of x is inverse function of exponential function. So thank you very much for being with me for a while, and see you in next video. And don't forget to subscribe to my channel so that you can get notification for next video. Thank you very much, and see you.